Thank you so much for inviting me and IFE for this energy outreach. I'm working at the Institute for Energy Technology, IFE. We're about 600 employees and working within different technologies and energy fields. Some of them has been mentioned here today. In the oil and gas, we're doing a lot, and also together with UIS. And of course, talking about fission, IFE is the actor that has the 2 nuclear reactors in Norway. And what Richard was referring to today, the waste is coming from us, but through now a governmental agency that is taking over quite some of our employees, actually. Just shortly about me. I'm 40 years old. I grew up in Sandnes, so not far from here. Have my master's and the PhD from NTNU in material science, and I have been doing various stuff, but within solar for the master and PhD, and also I did a postdoc at the Arizona State University for a couple of years, and now I'm back as a research scientist at IFE, working in the Department of Solar Power Systems. I have a plan for this presentation, and it's to talk about solar power in 30 minutes. It brings up a lot of opportunities, actually. So I brought up some of my favorite topics. I'll tell you a little bit about market first, both globally and in Norway, just to put the frames. And then I'll touch upon some PV physics. There could have been chosen a lot of stuff. Of course, optics is a big thing in PV. I'll touch upon the electrical properties of the semiconductors here. And then on the challenges, I would like to touch upon some topics that really needs to come in place in order to roll out this energy technology in the world. And I'll also address some of the challenges there. Just showing you how things have been developing lately. The first graph there is showing the annual PV installations growing rapidly from the early 2000s. And the graph to the right is showing the cumulative PV installations. And you can see that we are about that 800 gigawatt power, gigawatt peak in the world now. And Richard said that you never give these numbers, you should always give the actual power. So if this was in Norway, I would just multiply it with 1,000, because that's the number of solar hours we have a year approximately in Norway. And then you would get up to then 800 terawatt hours. Which is somewhere like the 6-7-fold of the whole energy production in Norway. Just showing you a little bit about how the shares within renewable technologies in the world are. The yellow there is PV. And when I see PV, that's solar. That's short for photovoltaics. The dark blue is wind, and the light blue is hydro. And as you can see, the PV is gaining more shares, and will probably, as it is at this moment, the most cheap power source that we have, will only gain shares here. At the moment, the capacity that is installed in the world is corresponding to 3.7%. Of the energy demand of the world. This is expected to reach 25% by 2050. This is a graph that often is shown when talking about the PV market. It's a learning curve. It's showing the price reduction as a function of cumulative PV module shipments. You can think about installations there. And you can see it has been dropping rapidly, and it's actually dropping more rapid now than it used to. There are various incidents that has happened on this line. I won't go into detail there. But in short, you could say that for every doubling of the cumulative PV module shipment or installation, the average selling price is decreased by about 20%. Talking about solar power in Norway, this is not something that we have spent a lot of we've spent a lot of technical efforts on it. There are lots of companies in Norway that are exporting technology throughout the world, but politically we have not been using much efforts on this. It's probably going to be coming now. This governmental agency, NVE, has forecasted that by 2040, there will be 7 gigawatts of PV installed in Norway, which is, and they are not known to be very forward-leaned. So that's probably actually a conservative estimate. The solar energy cluster has estimated about 2 to 4 gigawatts by 2030, and that would correspond to a annual increase of installations of 20%. The potential for PV power on buildings is, however, very large, about 30 to 50 gigawatts, according to Multiconsult. And just commenting shortly on the why we would even consider PV in Norway, because we have lots of power, we have hydro and so on, but with these projections on how much energy we will be needing in 2040, 2050. We're going to be needing 30-40% more energy than we have now because of the electrification, because of more process industry. We have these battery factories coming, and now we even want to electrify the oil fields. So that's going to add on even more. Okay. Then I'll jump shortly into some PV physics. It's about the atoms and the electrons that we are very interested in here. So as you know, the electrons, they come in different energy states. And when the atoms become many, we regard them as in bands. And in the valence band, the band is filled with electrons, and they are not free to move. They are quite bounded to the protons in the core, and they need a lot of energy to get up to the conduction band where the electrons can move. We normally think of materials, or divide materials into 3 kinds of categories. We're talking about insulators, and that's where the energy gap between the valence band and the conduction band is so large that you will never get any external stimuli to be able to excite the electrons from the one band to the other, and so they are never conductive, electrical conductive. In the metals, the conduction band and the valence band, they are actually overlapping, and these materials are always conductive, always being able to conduct electricity. For the semiconductors, this is a special type of materials. There are not so many elements that are semiconductors by nature, but you could also make compounds of various elements that will have these properties. And there is a gap where you can actually use some external stimuli to excite electrons from one to the other, and suddenly get a conductive material that wasn't before. And this is a material, silicon is the one that has been used for solar power technology for many years already, and the market shares are not laying off there. It has a band gap of 1.1 electron volt. Alexander was talking a little bit about the kind of units these are. I will not go into it, but this corresponds to a wavelength of 1100 nanometers. I'll show you in a minute where that is in the solar spectrum. But the sun is shining on the material, kicking loose an electron, and then the electron is leaving behind a hole, which we also regard as a conducting element. We call it a charge carrier in the PV physics. And these two are wobbling around, and they will meet again, and they'll recombine, and you have not used any of that energy. So what one is doing, well, let me just show you the solar spectrum first. 1100 nanometers is, it's shown there. So all the wavelengths from the sun coming, which has a longer wavelength and a lower energy, these will just be lost. They will just be absorbed as heat, and they will not contribute to the electricity. So there's a limitation there with silicon. This is where the visible range of the solar radiation is. The colors. But in order to utilize these kicked out electrons from the sunlight hitting the semiconductor, we do something we call doping the materials. And what this is putting like 1 in a million, 1 in a billion elements from another element that has either one less electron or one more electron than the silicon itself. And by putting these elements into the lattice of the silicon, it's a rigid lattice, and some of them are then replaced by boron or phosphorus in this case. That's creating an electric field. And this is working as a diode where the charge carriers can only go in one direction. So, but by having one side doped with pluses and one with minuses, electrons and holes, you then create a diode where the electrons and the holes will be separated. And you can then, if you connect this to an outer circuit, you can utilize the electrons before they get back again and be combined. So that's how it's working. The purity of the silicon is one part of the PV technology that has been maybe had the most development, and is why the prices are reduced and why they are becoming better for every year. One needs this material to be extremely pure. When I started working with PV back in 2007, we were working with what we call multi-crystalline silicon, which is a way cheaper way of making silicon, where you don't have to have this perfect huge crystal, which you can imagine will take a lot of energy and to make. In the multicrystalline, you have grains in the structure, and they have nucleated, started growing from each of their spots, and then they'll meet, and there'll be a boundary between them where somehow impurities like to find themselves. So even though that kind of material was much less cheap, much more cheap to make, we still have landed on making this kind of monocrystalline silicon now, and that's what's I think is 90% of the market or something. But a solar cell is not only silicon. And this is a very simple architecture I'm going to show you here now. You have this slab of silicon in the middle, which is then doped. The slab is really a wafer, and it's about 140, 150 microns thick these days. So it's getting really, really thin and quite hard to do fabrication with, because they break. Someone has to have very good strategies and very good robots to handle them. Then there will be a back contact. These days, that one is not uniform behind. It's more like dots on the back, and they are put with lasers now. There will be an anti-reflection layer to absorb more of the light, and then there will be contacts. There will be a protective layer, and when you put these cells into modules, there will be glass on the front side, and there will be a backsheet behind. So there are quite many kinds of materials involved in the battery. And just to touch upon some of the areas where one has been doing a lot of research lately, and this is also the reason why efficiencies are developing these days. For the silicon, as I mentioned, we are limited to this red part of the solar spectrum in terms of getting power out of the solar cell. And this is due to the band gap. But if we could, and then there is a theoretical limit there at 30% for a silicon solar cell. This is also a chart that everybody is showing all the technologies and how they have been developing in terms of efficiency over the last years. And as you can see, if we draw the line there of the theoretical efficiency of silicon solar cells, there are still some technologies that are going beyond here. And those are multi-junction solar cells. And they exploit that if you put together and you stack various materials with various band gaps, then you can design a solar cell that will be able to utilize more parts of the solar spectrum, and of course get way higher efficiencies than if you only use silicon. But you don't do this for free, so it comes with a cost. So here everything is about large-scale production in finding ways of doing things cheap. Another thing that there's paid quite a lot of attention to is this part of the solar spectrum, which is not used within the silicon technologies either, because here the photons have a lot of energy, but you only use the part of the energy that is needed to kick up the electron from the valence to the conduction band. And one way of trying to utilize this part of the spectrum is to split the photon coming in into two photons, and then make both of them contribute to exciting an electron each. And that would double the efficiency if you could would do that properly. Transparent contacts is a big thing. The contacts here, these are kinds of conventional contacts for solar cells. They're made of silver. And you can see all the area that is covered here is lost in terms of producing energy. You need to hit the blue part or the black part. So if one could make these ones transparent, you would increase the efficiency quite a lot. And there are lots of materials and physics into that. Titanium oxides and various parts. Yeah, I will not go into it. Just to show you a little bit about the trends going forward in the technologies. Here is a graph showing silicon modules. As you can see, where we will come in 2030 with these conventional technologies is about 23%. You might think that sounds very little, but remember this is for modules. So in modules, you put together cells, 72 cells up to 100 cells, and you will have some losses there due to ohmic losses in contacts and so on. So the cells themselves, they are 2 to 3% higher. So 23 for this kind of technology is what we're aiming for in what is foreseen and predicted there. There is one other technology where you have a multi-junction cell, a tandem cell, so it's 2 layers, but both layers are with silicon. I think the upper layer is made of amorphous silicon, which has another band gap. This graph is showing some of the other tandem solar cells where you have also introduced another kind of material. Perovskites are very popular to do research on and have been for quite some time now. The challenge there is to make the perovskite being as stable as the silicon. When you make silicon solar cells and you sell them, you give a guarantee for 25, 30 years because the material is so stable and it degrades so little. That you can do that, but the perovskite material is a little bit more of a different kind. So the research now is trying to make that one as stable as the silicon, because it wouldn't make sense to start selling PV modules that has a lifetime of 15 years, for example. And this one I also wanted to show you. Big thing coming now are bifacial solar cells. They are producing energy from both sides, and it doesn't cost very much more to make these kinds of cells. So that's something that's really coming now. A normal bifacial gain would be 17%. It depends very much on what you have on the ground. If it's gravel, then it's going to be lower. If it's water, it's going to be a lot more. But there are a lot of research on what kinds of membranes you could, for example, have on your roof and put this on, and then you will have quite a lot more power production than you would have. Also in Norway, this is something we're looking at from another perspective, because the sun is quite low on the horizon. So actually putting the solar cells vertical and east-west oriented would make us produce power in the morning and in the afternoon, and that's where when the demand is. Of course, the net power production throughout the year would be lower, but in these times, producing the energy when we need it is actually more important than the net production. And as you can see, these bifacials, they're going to be almost taking over the market by 2030. I just wanted to show you this too, because this is important. We're going to educate a lot of people in data science. Here you can see that for machine learning in process machinery and logistics systems, we have basically none at this point. And one is projecting that 80–90% of the manufacturers will have this kind of technology in 10 years only. So there will be a lot of data scientists out there. And this is going to, of course, make the modules even cheaper. All right, I'll go for the challenges, and I spent 20 minutes. Okay. Challenge number one: intermittency. I don't know how familiar you are with this word, but it means that PV and wind, especially, they're producing power when there is sun and wind, and not at other times of the day. For Europe, there has been quite a lot of studies, and this study I like. It's looked at the conditions, the weather conditions, throughout 3 years, and mapped them over the months, and plotted a capacity factor there, which is power over effect. The best you can get is 0.35, which is not very it's not very high, but that's how it is with PV. This was also something Richard pointed out. And the profile throughout the year is looking something like this. For Norway, it's actually not that much worse, even though we have less sun in the winter. But the cooling of the temperature plays a big role in PV. The cooler the module temperature, the higher is the efficiency. And we're also working with the snow, and there are different strategies of not having snow covering the panels throughout the winter. And one thing we often think is that maybe if we can use wind power, this in combination with solar, this could be complementary. And from this chart, it really looks like they are quite complementary. Here you can see that it's another kinds of scale. It's not a capacity factor anymore. I want to go into that. But it's not as simple as this. Even though there are more wind in the winter than in the summer, if you look at the week and the daily and hourly production, and you do a correlation study of that, you can see that on a daily correlation, the max you can get is 0.20 in correlation. If you had -1, that would be perfect opposite correlation. That would have been, then we wouldn't have needed anything else than wind and solar. But the real truth is not as simple as that. And if you go on an hourly basis, it's even lower. So this is just an example of how a day could look. You have typically power demand, which is rising in the morning and in the evening. The sun is at its highest at 12 p.m. every day. So that's when you have the most power production from the sun. And the wind is, of course, can be various profiles throughout the day, but typically at night it's there are more wind. So what do we do about these parts where we don't have any PV or any wind power? Well, we have to either use other kinds of technology. Hydro in Norway would be a good thing. Gas, base loads like nuclear and coal wouldn't do too good here. But there are other ways to handle this too, and that's through storage and peak shaving, peak shifting. There are various things that you can go into here. There are very interesting things, all of them. But looking into that and creating this energy system that can optimize and utilize all these energy technologies that we have then implemented and installed, we need lots of prediction. And here is a huge job for physicists. And at IFE, we're spending a lot of time on this. So we need to be able to predict the PV production, the wind production, the demand load, electricity prices, uncertainties, and what have you. For the PV production forecasting, we have various strategies depending on if it's long-term or short-term. We can forecast and predict on a weekly basis, on a daily basis, hourly, minute, and we use different kinds of meteorological data, experience data, historical data, learning curves, and sky cameras for the most where we really want to know if there's coming a cloud and we want to charge our battery when before that cloud is coming, then we need to know, and that's when you use a sky camera. So that's one challenge that a lot of people are going to be working with, and it's extremely interesting. And you're also working for the society and in the intersection between science, social science, and politics. Very interesting. I want to touch upon circularity. I only have one slide on this, but I think it's important. With all this PV technology being rolled out in parks like this, there's going to be tremendous amounts of waste at some point. And we need to be in forefront to be able to handle this waste. And we don't want to have waste. We want to use it again, either as recycle, reuse, upcycle, all of these things. And we need already now to have the strategies for how to handle this. And as you can see, it's not only silicon. There's lots of different elements going into this, and these are more or less abundant on the Earth. And I think, especially together with the developments in the battery technologies now, this is going to be something that a lot of technologists are going to be working with in the time to come. There's a funny ad. It's from an American mining company, so they just want to mine more. But this is not really how we should think. And the last challenge I want to touch upon is social acceptance. You would maybe not think that this is something that we have to care too much about when it comes to PV, but the land areas that are used, they're massive. And one needs to be careful about what kind of land one is using. So here, suddenly the municipality of Gjøvik came out with an article through NRK on that they're going to be building a solar park. And already in the ingress of the article says that people are skeptical. So one needs to move very carefully in this segment. And there will be different interests, and not everybody is going to be seeing the needs for more energy. One should really think about if we need to build up more of our nature and how this is done. Food land that is used to produce food is highly discussable if one should use for this kind of energy production. But it's going to be interesting to see. We are also looking into, it's a big field actually, agro PV, generating power on the farmlands together with growing crops. But one kind of installation that has not been so discussed, and I think everybody is agreeing that this is a good idea, is using big industry rooftop flat roofs for PV. This is the ASKO warehouse storage in Vestby, and you can see they've built out quite a lot here already. They're going to also be building out this because they're going to be electrifying their whole car fleet by 2026. So they're going to have a huge charging station here, and they're going to be needing more power. Another way of thinking is to combine the PV installations with green roofs. This is something that's becoming more and more popular in big cities where one has built down almost all the green areas. This is a kind of green roof that I think it's actually produced here in Stavanger. It's called bergknapp or something like that. It's really, really nice. It looks like this coastal kind of flora, and it's not growing very high. So it's not a competitor to the sunlight with the PV panels. And it has one very important mission too, and that's the handling of heavy rainfalls, which is a big problem in big cities. So this is the way of combining things. This is a good example of nicely integrated, building integrated photovoltaics. This is Brattørkaia in Trondheim. Very nice, not very cheap to build, but it functions well as an example of how it could be done. And building integrated PV is something that's coming more and more. It's a little bit stuck in between that architects wants to have all kinds of colors and physicists wants to have them as dark as possible because that's when you absorb light. So nobody has really been able to break the code on mass producing this because people want different stuff. But it's probably coming. And then the last thing I wanted to show you, and this is something that is also coming, and there are a couple of Norwegian companies doing very well in this field, floating PV. It has some benefits that are worth to mention. First of all, in big cities, they are often located close to water, but with not much room on land to build out power production. And this is highly mobile, can be transported, and you can add on for power production to cities. The water is cooling down the PV panels, so they're actually have a higher efficiency than they would have if they were on land. But maybe the one place that it's used most of all is on hydro power dams. There is already the electricity infrastructure to take the power, and they are perfectly complementary because when the sun is not shining, you can open the valves and produce hydropower. Also, in some parts of the world, it has the mission of reducing the evaporation of the water, which is in California, for example, that's a big thing. So that was what I wanted to tell you, I think. Yeah, thank you for listening. How did I do on time? Well, a little bit over. Thanks.
Thank you very much, Tine. If people have questions, please put them in the Q&A. First question is silicon the most efficient element for converting sunlight, or is it just the cheapest?
It's just the cheapest.
What would be the most efficient? You mentioned about gallium arsenide at some point. And
gallium arsenide is the one that they started out with when they used it. Well, PV was developed for space first of all, and that's what they used then. But it's not cheap to make, no.
Another question we have is Norway going for solar panel fields outside Norway, or is it going to support citizens in Norway or outside to make their own installations at home?
It's Norway.
Yes.
Well, Norwegian companies are exporting, they're making and selling and actually running large PV plants abroad. So Scatec is a really big company doing this. And there are companies also installing PV panels on your roofs, but none of these panels are made in Norway. Although the silicon is made in Norway because Norway has had a tradition for being a silicon producer, but the assembly of the cells and the panels, that's typically happening in Asia, but it's something that Europe would like to take back at some point. Yeah, but it's quite a big industry in Norway now, even though we don't see it because we're not installing it here, but it might come.
Sorry, that was a clarification from Diana. She means about government plans for this installation.
So
the Norwegian government supporting this?
So NVE, they have made a prediction that there will be about 7 gigawatts installed PV power by 2040.
You mentioned about the possibility of putting these cells vertically. Is the idea then that they would be fixed vertically, or can you allow them to kind of move? Is it efficient to have them move with some electric motors or something that?
Well, then you will be introducing movable parts, right? And that just increases the cost enormously. But tracking systems, you have technologies that tracks the sun so that the panel is facing the sun 90 degrees at all times during the day. And of course, these are producing a lot of power, but those systems are expensive, and also having movable parts in our kinds of conditions. Well, also in deserts, that's a problem. So they break. They don't have 30 years of lifetime.
Do we have any other questions from in the room? Oh, yes, we do. This is a question from Simon Walker. I know they are planning on solar panels in Longyearbyen and shutting down the remaining coal plant. Can you comment on the challenges on Svalbard?
Yes. They are planning to really put PV panels on all their buildings, which would definitely contribute to producing power. But of course, you need to have other kinds of either storage, or you need to have other kinds of electricity production. So I think what they're thinking of there, and that's going to be very interesting to follow, is to have seasonal storage in the mountain next to Longyearbyen, where they will probably then be storing heat, which then will be taken out during winter. And I don't know if it's steam turbines or what they're going to be using, but yeah, I think they first need to get the acceptance from the Norwegian government of doing that kind of installations in the mountain there, and yeah, let's see how that goes.